Welcome to this video presentation by the postgraduate student whose poster it represents. We will miss the bustling crowds around the posters at the All Energy Conference this year, but we hope you enjoyed this online version that we have created. Before the presentation starts, I would like to acknowledge the support of our generous sponsors. Without this support, the competition could not proceed and the winning entrants would not receive a financial award. Our platinum sponsor is the Victorian Government through the Department of Environment, Land, Water and Planning. Its brands include Victorian Energy Compare, Victorian Energy Saver, Victorian Energy Upgrade Program, Energy Scorecard and Energy for Business. Their contact details are on the slide. Monash University's Monash Energy Institute is one of our silver sponsors. With over 170 staff involved, the Institute has a vision to bring people together to solve global energy problems. The Monash student posters in this competition represent some of that work. Baywa Renewable Energy is another silver sponsor. Baywa develops both wind and solar projects in Australia as part of a global energy portfolio. Baywa staff have also supported our AIE events in the past, including our Young Energy Professionals Speed Networking events. Our final silver sponsor is the University of Melbourne's Melbourne Energy Institute. Many of you will have attended their regular forums that keep the energy community and public up to date on technical and policy energy matters, and the University of Melbourne posters in this competition reflect some of that work. Seed Advisory is our bronze sponsor, and this small but well-recognised energy consultancy covers both the technical and regulatory fields. Seed Advisory has been a regular supporter of the AIE and a presenter at our events. Lastly, we thank All Energy for hosting our live poster events over the last decade, and we look forward to doing this again post-COVID. These last slides show you our poster winners in the last competition. And I now hand you over to the poster presentation. Thank you.
Hi everyone, my name is Dillon. I'm at the University of Melbourne. And this work was done in collaboration with my supervisor, Professor Nando Ochoa from the University of Melbourne as well. And today we're going to talk about how we can unlock more primary frequency response from residential batteries using active droops. So let's get straight into it. Batteries that customers are adopting, they're installed for self-consumption. What this means is that it charges from the excess PV generation and then it discharges to meet the local demand. And in theory, they can inject at any time. However, there are export limits that restrict this operation. And this limits the amount of primary frequency response using fixed droops during these high PV generation times because you have this export limit. Now, what we propose is that we can use the power of smart meter and get that information as well as the information from the batteries to calculate active droop settings to get more out of these batteries. A little bit more on how this process works is depicted in this flow chart on the right hand side, and we'll go through step by step to see what's happening to get an overview of the process. We have this term we call the battery manager, and it calculates the true ability of batteries to provide active power or to provide primary frequency response. And it does this by using the export limit, as well as the information from the customers from their smart meters and from their batteries. So things like the energy and power ratings of the battery, the actual discharging and charging power of the battery. And then the system operator communicates an amount of PFR that it wants to use that is responding to this PFR trueability calculation. And finally, we can calculate and broadcast droop settings for each individual customer. Let's look at a case study with 73,000 customers. The ATR is the ability to respond, and it's a metric that gives you a value or representation of how much primary frequency response each battery can provide in relation to what was requested from the system operator. And greater than 100% is desirable because it means that you can do more than what was requested by the system operator. And if we look here, during high PV generation times, the ATR, or the ability to respond, is very low, and that's because we have a lot of PVs being generating at that point in time, and then they start approaching the export limit, and then the ability to respond reduces. However, if we look at the parts on top, some of the batteries can indeed do more, and that's the beauty of the methodology. It capitalizes, or it exploits this extra ability from these batteries to provide more. And if we look at a comparison between a fixed droop and our active droop, we can see from the frequency performance here, we have a far better performance in terms of reaching that 4.90 target for the frequency. And then if we look at the megawatt response, so this is aggregated from all the individual customers and we sum them up, we can see a very similar thing happening here, where the fixed droop does not provide as much power as the active droop, and it does not yield the frequency performance we see from the active droop methodology. So to summarize this active droop methodology that we have, it unlocks more of the potential from these batteries. If we look at a voltage analysis that we performed a power flow for a medium voltage, low voltage realistic network here in Australia, we have this effect. We're seeing that even though we're using the active droop methodology and having more reverse power flows from the batteries, we're not having any voltage issues. I mean, at least for this particular network. And what this means is that we can have more of this active power being provided without affecting the integrity of the distribution networks. And then we can see that the fixed export limits are too conservative, and then we can actually get more out of these batteries. And as a matter of fact, this is performed in some future work, which I'm happy to discuss if you guys want to hear more about it. So to conclude, we have reduced PFR resources resulting from the increase of renewables in the system, and this is becoming a concern for process system operators. The active droop methodology that we propose has the ability to unlock large amounts of this PFR by using those measurements and information from the batteries. And then it shows that we can provide superb PFR after contingency without affecting the performance of the distribution network. Ultimately, we aim for this work to provide some sort of evidence for adopting new industry standards involving batteries and help have more of them on the network, and then have them help the networks as well. Thank you very much.